Thank you, Yep. My name is Manish Gupta, and this paper is on detoxifying query auto-completions, the auto-suggest thing. And this is in collaboration with Aishwarya, Kaushal, and Professor Maunendra, Desarkar from IIT Hyderabad. I work at Microsoft, right? So this is a good academic industry collaboration in that sense, right? So, I mean, especially this one is an example of how academia and industry can work together. Academia typically does not have query auto-completion data, and industry always needs good researchers to collaborate with, right? So that's that. There is a huge lot of toxicity in NLG outputs. Of course, for query auto-completions, typically you really need to use natural language generative mechanisms. You already have lots of queries that users have put up, and you actually try to recommend completions for those prefixes using tries which are built on previous query logs. However, so as to be able to enable suggestions even when tries don't really give you any good suggestions, you basically use natural language generation mechanisms. These NLG models are, of course, pre-trained on unfiltered corpora, and therefore can actually end up generating really bad suggestions, right? Offensive ones, toxic ones, specifically, that I'm going to talk in this discussion, right? What do I mean by detoxification? I basically mean that we want to do some sort of a controlled text generation where, given a session and a user query prefix, you want to generate 10 completions which are, of course, close to the actual complete query queue, and they're relevant to the session, so relevance has to be guaranteed. But at the same time, what you want to do is to really do this, generate non-toxic completions, right? That's that. So why is detoxification challenging? Well, the point is that when you're generating these things, the queries are very short in nature. So this shortness of queries, which can potentially also contain spelling errors, and the queries disregard grammatical rules and so on. So therefore, using these so as to be able to generate non-toxic completions is challenging, specifically when the input prefix itself is essentially toxic in nature, right? So, so the queries can be, people can be typing in all kinds of not clear words as well. So there are various kinds of queries. There could be obvious toxic queries with very, very toxic keywords. There could be non-toxic queries. And then there are other categories in general. So most people have looked at this problem only from a toxic versus non-toxic perspective. But this new third category, we actually call it addressable toxic. So the point is that it could have implicit toxicity. So for example, how to become a perfect liar, right? Or subjective toxicity, so black representation in the media in that senses, or non-toxic, but does include some sort of toxic keywords, typically which are related with toxic keywords, right? So, and what we want to do is to essentially enable good completions while ensuring that addressable toxicity cases are addressed as best as possible. So if you really look at this example, this is a session of the user, right? A pretty reasonable, genuine, non-toxic session in that senses. And then this is a prefix, how to be, right? And how to, and this is the actual query the user put up. But then if you look at baseline systems, they actually generate, some of them generate reasonable things, but some of them can actually generate partially toxic kind of things. But our system really generates reasonable outputs. Now, if you look at another kind of a user, so a pretty toxic session in that sense is, and then there is a prefix, and then the intent, the original query intent is also toxic in nature. But hey, while suggesting we should try to avoid toxic suggestions, unfortunately, the baseline models cannot do that. However, our model, even in this toxic case, even in the case where the input prefix and the session is toxic in nature, ends up generating non-toxic and reasonable outputs. Okay? So in literature, there are several approaches that are proposed to generate non-toxic things. In fact, in the industry, a typical way of handling this is just have block lists, right? So essentially have block lists of offensive terms, have your red teams essentially create these lists. And users can also be used to really create these lists. They can actually report feedback and so on, right? However, maintaining these query templates is difficult. Coverage always remains limited. New things keep coming in, right? And therefore, we want machine learning methods. And people have come up with various machine learning methods as well. They have designed query embeddings. They have designed n-strike rules and so on, right? Several other things have come up. The most relevant work most relevant community work, which is relevant to our work, It's basically controlled text generation. So people have tried to do controlled text generation for other scenarios, like controlling clickbaitiness of the output, controlling whether it is formal style versus an informal kind of a tone and so on. So people have done various kinds of things, and the way people have done them is by steering the generation while decoding in general. So you have a single model, but while decoding, you basically try to steer it in a direction that you want to. Right. People have also tried reinforcement learning, right? And what we do is to, of course, compare. We basically tried these approaches, saw how they worked, and then figured out that there are some challenges because of which they don't really perform as well, and therefore propose our method called as detoxifying query autocompletion, or the DAC method. Okay. So our method basically consists of some components that you see here. The first part is to really create a reasonable personalized language model. Remember, queries are very different from the standard documents on which the popular language models are trained. So therefore, we needed to actually train something that works on queries and something that can be used for personalization, right? So therefore, we train a personalized language model. Then to be able to detect, to be able to generate non-toxic outputs, we need some detector as well, something that tells us that, hey, the output that you're generating is reasonable or toxic, or it's non-toxic or toxic, right? And therefore, we create a T classifier, the toxicity classifier, which basically looks at queries or looks at generations and then tells whether it is toxic, non-toxic, or addressable toxic, a ternary kind of classifier in that sense, right? Then we essentially have these three phases in our approach: exploration phase, which basically uses personalized generation with this personalized language model that we have. Right? Then we have a quantized optimal transport phase, which basically tries to understand the toxicity if you use these, if you looked at this personalized language models generation, right? And then, based on the scores that it provides to the output that is generated, initial output generated by this personalized language model, it sort of tries to learn and update the parameters of this personalized language generation model such that it learns to generate non-toxic stuff. Okay. So in some ways, this learning mechanism is about giving feedback based on whatever is created by the initial personalized language model, using the reward model, using the reward component that you see here. In fact, we have three different reward components. As you see, the toxicity of the generation, we have the length penalty, and we also have the optimal transport score. And more about the optimal transport score I'm going to talk about in the next slide. Okay. So yes, we have a toxicity classifier. There are existing models which can do this. However, what we want to do is not just binary classification. We want to do ternary classification. So therefore, we generate this T classifier, toxicity classifier, trained on reasonably large data sets from Bing. So remember, I told I work for Microsoft. So we have like large data sets at Bing, where we have toxicity, non-toxic, and addressable toxic three classes. We take these large data sets and basically train a toxicity classifier. This classifier is really good. It basically gives you about 0.8 correlation with the Detoxify, a popularly available public classifier, on these two classes, the non-toxic class and the toxic class. Detoxify doesn't have an addressable toxicity class, but we do reasonably well even on that class. Okay. Now, the other part is detoxification with reinforcement learning. So remember, there is the exploration phase, which basically generates some output from initial output from the personalized language model. And then we have this quantized optimal transport phase, which provides the reward scores, which can be used by this learning component to update the weights of the personalized language model. Okay. So in that sense, we basically use reinforcement learning for this learning phase. And the reward, the optimal transport score, is basically obtained using this block. Okay. So essentially, we take the initial policy, which is the personalized language model. We take the training samples, and so we take a batch of these training samples. For every batch, we basically generate the output from the personalized language model, generate the completions from that one, and then we, of course, append the completion, the overall completion in prefix plus the generation to this. But then more importantly, we actually compute this quantized reward score. Okay. This reward score basically is used with the PPO reinforcement learning algorithm so as to update the parameters of the personalized language model. Okay. Now, what are the reward models that we use, right? So we actually use three different rewards, basically. One of them is based on the optimal transport, and then the other two are essentially the length penalty and the length penalty that you see here, the length penalty and the toxicity score, right? So length penalty and the toxicity score are sort of standard. What I'll do is to sort of spend more time on the optimal transport score. Okay. So the way we do this is essentially we say that there is a normalized quantized score. So the optimal transport score that we're going to compute is going to be Q base plus Q intensity divided by 3. So the idea is that we want to have rewards such that they lie in different ranges. So for each of those classes. So if the generation from the personalized language model is non-toxic, no reward, right? I mean, essentially, you don't need to basically penalize it for anything. But if it is toxic, then we want to do a heavy penalization. And if it is basically addressable toxic, then we want to do milder penalization. And that is why we have two components to the reward, the Q base and the Q intensity. Q base is set to 0, 1 by 3, or 2 by 3, depending on the class being toxic, non-toxic, or addressable toxic. Q intensity is basically the probability of predicted toxicity class. So if it is essentially non-toxic, then it basically tells you the probability of it being non-toxic, and if it is addressable toxic, probability of being toxic and addressable toxic, and so on. Okay. So that's that. So essentially, we take all of these three and then sort of normalize this quantized scores. What we also do is to use, I mean, based on these reward scores, right? We also use this quantization matrix. This quantization matrix basically says what it tries to encode is that if your if your generation is non-toxic completely, then essentially just care for lexical similarity between the actual output, and whatever is generated. Right? But if the query was toxic by itself, then don't care about matching with the actual output because it was toxic in nature. Rather, care about trying to generate an alternate output which is non-toxic in nature. Right? So that's the idea. The idea is that if you basically have the query as toxic, then you want to move away lexically from the query and generate non-toxic stuff. Okay? So yeah, I mean now, so based on this, we basically did several experiments on two data sets. One is essentially a Bing data set, and the other is an AOL public data set that we have. Given the amount of time, I'll not go into details about these data sets, but we did the nice division into train, validation, test, and so on. And we compare with many, many baselines. So domain adaptive pre-training baseline, PPLM, which is a very popular model for controlled text generation, Quark and PPO and fine-grained RL, which are like RL-based mechanisms for reinforcement learning-based mechanisms. Right? So here are our main results essentially. So, and you see there are three tables. So one is for toxic class. So, toxic, addressable toxic, and non-toxic test sets. Right? And of course, these test sets are across Bing and AOL. So we have both of them. What kind of results do we show here? So we show two different kinds of metrics. One are in terms of fidelity with the actual ground truth output. Okay? So which is basically being shown in the standard MRR and SBMRR kind of matrix. So SBMRR is a special kind of MRR. Let's not get into those details, lack of time, right? And we also have the blue kind of matrix. So they basically measure how close we are to the actual output, right? And then there are toxicity-based metrics as well. So using Detoxify our classifier and also Detoxify as the public toxicity classifier. And what you observe is that across all the three sets, our method gives you a very good trade-off between lexically matching with the actual ground truth versus being less toxic as much as possible. Okay? So there are more examples to show interpretability about how our method slowly moves from toxic class towards non-toxic class over iterations. Especially when you are looking at toxic queries and so on. So I'll skip the details, but in summary, what I want to tell you is that a contribution in this paper was to establish and find out that sweet spot between lexically matching with the actual query output and generating non-toxic outputs. So somehow being able to basically get that by using an optimal transport mechanism, as I talked about. Right? So our method, DAC, essentially included three important components: exploration, quantized optimal transport to come up with a good reward score, and then reinforcement learning to be able to make use of that reward score to update the personalized language model. And we tested on Bing and AOL, two different data sets. One is proprietary, the other is public, and showed better results compared to existing models for controlled text generation. Okay? That's it. I think I'll stop here and take questions.